So welcome guys. This session will be looking at steroid hormones, especially the steroid hormone synthesis of aldosterone and cortisol. I know you have other steroid hormones such as your testosterone, um, progesterone, your estradiol, but today we'll be looking at the steroid hormone synthesis, especially in the adrenal cortex, especially the two outer zones of the adrenal cortex, that is your zona glomerulosa and zona fasciculata. In your zona glomerulosa, you have the synthesis of the mineralocorticoids, with the aldosterone being the main mineralocorticoid in human, and in the zona fasciculata, you have synthesis of glucocorticoids, with cortisol being the main glucocorticoid in man. Now, we also look at congenital adrenal hyperplasias to finish. So welcome all, my name is Oris Munye and I'm the Daktari. Now, let's start with this now. Steroid hormone. Cholesterol is the precursor of all classes of steroid hormones, be it the glucocorticoids, with cortisol being the main example, mineralocorticoids, aldosterone, and the sex hormones such as the androgens. In androgens, you can have testosterone as an example, but we have adrenal androgens produced by the zona reticularis. You also have estrogens and progestins, okay? Now, note that glucocorticoids and mineralocorticoids, collectively, they are known as the corticosteroids, okay? Because they are produced in the adrenal cortex, okay? Now, synthesis and secretion occur in the adrenal cortex, that is, your cortisol from your zona fasciculata, aldosterone from your zona glomerulosa. The adrenal androgens come from the zona reticularis. Also, the ovaries and placenta, they will give you your estrogens and progestins, and the testes will give you testosterone. Okay, now steroid hormones are usually transported from the blood, are usually transported by the blood from the site of synthesis to the target organ, because they are hormones. So hormones will always be transported by the blood. Now, because of their hydrophobicity, they are lipophilic, that is, they must be complexed with plasma proteins. Albumin can act as a non-specific carrier and thus carry aldosterone. However, we have specific steroid carrier plasma proteins that bind the steroid hormones more avidly than albumin. For example, your corticosteroid binding globulin, also known as your transcortin. As the name suggests, it will be used for transporting cortisol. Now, you have a number of genetic diseases that are caused by deficiency in specific steps in the biosynthesis of steroid hormones, and these deficiencies will lead to the congenital adrenal hyperplasias. Now, you can see this is your cholesterol here. Let me take a pen and remind you, I've done a good video on cholesterol. So, these are your steroid nuclei. This is A, B, C, and your D here. Then you can see the side chain here. This is your side chain, okay? Then when naming the carbons, this was carbon number 1 here. I want you just to remember 2, 3. Please remember this 3, and you can see it is to the third carbon on the steroid nucleus A. That is where you have a hydroxy group attached. Then this will be 4. Sorry, this will be 4 here. Then this 5, 6, 7, 8, 9, 10. Then this will be your 11, 12, 13, 14. Then here 15, 16, then 17. So the side chain is attached to the carbon number 17. Then this will be 18 at this position, 18, and this 19. Okay, this will be a 19. Then on the side chain, this will be a 20. This, then 21, 22, 23, 24, 25, yeah, 26, then the last is here, 27. So it has 27 carbons. And how many hydrogens? 46, okay? And you can see only one oxygen here. Then can see cholesterol is converted first to pregnenolone. Then pregnenolone is the one which is now there, which gives rise to the other steroid hormones such as your cortisol, aldosterone, estradiol, testosterone. Okay, so that is that. So please understand this numbering here because it is very important, especially when you come to synthesis. Now, synthesis will involve the shortening of the hydrocarbon chain, that side chain I showed you of cholesterol, and then we will hydroxylate the steroid nuclei. Okay. Now, the initial and rate limiting, please understand this. The initial and rate limiting reaction will convert cholesterol to a 21 carbon pregnenolone. Okay. So cholesterol had how many carbons? 27, but we cleave the side chain to remain with a 21 carbon compound known as pregnenolone. Okay. This is catalyzed by the cholesterol side chain cleavage enzyme, which is a member of the cytochrome P450 mixed function oxidases, and it is found in the inner mitochondrial membrane, and it is also known as the P450 SCC. So SCC is a side chain cleavage enzyme, or you can find other text calling it a desmolase, okay, or even a lyase. Okay. Now, NADPH and oxygen are usually required for that reaction. Remember the cytochromes, okay? It is a hemoprotein. You require the NADPH and the oxygen. One oxygen is added and the other one is lost. It is a monooxygenase, if you can remember that. A monooxygenase, they add one oxygen to the compound. Now, the cholesterol substrate can be new. That cholesterol can be either newly synthesized. I've done a video on the de novo synthesis of cholesterol. Can also be taken up from lipoproteins, okay? And also can be released from cholesterol esters, which are found in the cytosol of the steroidogenic tissue by action of the esterase. So how does cholesterol get into that tissue? So there are either 3 ways in which cholesterol sources. So cholesterol can be either from the de novo synthesis in the liver, okay, or from lipoproteins circulating the blood, or can be released from cholesterol esters, which are stored in the cytosol of the steroidogenic tissue, and the cholesterol is released from the cholesterol esters by the action of the esterase enzyme. Then the cholesterol moves out, moves to the outer mitochondrial membrane. Then we have an important control point, which is the subsequent movement from the outer to the inner mitochondrial membrane. Remember, the P450 SCC, the cholesterol side chain cleavage enzyme, is found in the inner mitochondrial membrane. So we must move this cholesterol from the cytosol to the inner mitochondrial membrane. And this, for us to move across the inner mitochondrial membrane, we must have this protein known as the steroidogenic acute regulatory protein, your STAR protein, your STAR. Okay. Now, pregnenolone is the parent compound of all steroid hormones. It is oxidized and then isomerized to progesterone, which is further then modified to other steroid hormones by CYP, protein catalyzed hydroxylation reaction in the smooth endoplasmic reticulum and others in the mitochondria. I will show you that in the next slide. Now, a defect in the activity or any amount of the enzyme in this pathway can lead to a deficiency in the synthesis of hormones beyond the affected step. Now, to an excess in the hormones or metabolites that before that step. This means that if you have a deficiency in an enzyme, we will have accumulation of the intermediates before the deficiency of that enzyme, but a deficiency in the enzymes which occur after, which are catabolized by, which is catalyzed by that enzyme. So I'll be showing you that when we will be looking at the congenital adrenal hyperplasias. Now, because all members of the pathway have important biologic activity, serious metabolic imbalances occur with enzyme deficiency. Now, collectively, these disorders are known as the congenital adrenal hyperplasias. Hyperplasia meaning that the adrenal gland will be large in size. Why? Because they result in enlarged adrenals. Now, why is the adrenal gland enlarged? Because if you have deficiency of cortisol, remember cortisol usually exert a negative feedback to the corticotrophs of the adrenal hypophysis to reduce secretion of adrenocorticotropic hormone. But if you have deficiency of cortisol, there will be no negative feedback. So the levels of ACTH will be high, and this will cause a trophic effect on the adrenal cortex. So the adrenal gland will be enlarged. Now, Addison disease is an autoimmune disease where we have destruction of the adrenal cortex, and usually is usually characterized by adrenocortical insufficiency. Now, let's see. Now here we are. Please get to know this now. Here you have your cholesterol. Okay. Then in red, any enzyme which you see in this color is mitochondrial, and the others are found in the smooth, are microsomal. They are found in the smooth endoplasmic reticulum. Okay. Then I want you to note that all the others which are in the smooth endoplasmic reticulum, all of them are cytochrome, members of the cytochrome P450 monooxygenase system. Apart from this enzyme here, the 3-beta hydroxysteroid dehydrogenase, it is not a member of the CYP. Please remember that. Okay. Then let's look at this. And we will mainly focus on the aldosterone synthesis and cortisol synthesis. The others we will look another time later. Now let's start for aldosterone. We will start here with cholesterol, okay? And as aldosterone synthesis will occur in the zona glomerulosa, okay? Zona glomerulosa. That is where you have your mineralocorticoid synthesis. We start with cholesterol, okay? Cholesterol, then we cleave the side chain by the cholesterol side chain cleavage enzyme, or the CYP 450 SEC, or your desmolase, okay? And it is the rate limiting step or the committed step, okay? And this step is the one which is controlled by ACTH for cortisol, okay? When you want to increase cortisol production, ACTH will act here. But this step is not the one which is controlled in case of aldosterone. Okay, I will show you where aldosterone regulation, aldosterone synthesis regulation occurs. Now, once cholesterol side chain is cleaved, you can see here it is cleaved. Okay. It is, in fact, we remove at this position here. We cleave this from 22 to 27 is removed. You remain with your pregnenolone. Then pregnenolone will be converted by the 3-beta hydroxysteroid dehydrogenase to your progesterone. Okay. So why it is called 3-beta hydroxysteroid dehydrogenase? Because you can see at position number 3, we remove that hydrogen here. Okay. Then the progesterone will be converted to your deoxycorticosterone by the 21 hydroxylase, shown at position number 21 here. At 21 was, you can see we are adding a hydroxy group. So it is a hydroxylase. Then your deoxycorticosterone will be converted to your corticosterone by the 11-beta hydroxylase. And see at position number 11, you are adding another hydroxy group. So it is your 11-beta hydroxylase, and more importantly, it is a mitochondrial enzyme. Okay. Then your corticosterone will be converted to aldosterone by another enzyme known as the aldosterone synthase. Okay. Note this, that we have an enzyme, you might come across an enzyme known as 18 hydroxylase. 18 hydroxylase has both aldosterone synthase and 11-beta hydroxylase activities. Please note that. So if you have 18 hydroxylase will convert deoxycorticosterone direct to aldosterone. Okay, it has both aldosterone synthase and 11 beta hydroxylase activities. Now let's look at how you will synthesize your cortisol. Once you form your pregnenolone, you must first convert it to your 17 alpha hydroxy pregnenolone. So at position number 17, you add a hydroxy group, and the enzyme responsible is your 17 alpha hydroxylase. Okay, then once you form your 17 alpha hydroxy pregnenolone, you still have to carry out the dehydrogenation step at position number 3, and the enzyme there will be your 3 beta, this 3 beta hydroxysteroid dehydrogenase. Okay, and remember, this is not a member of the CYP. Okay, also another way which you can form cortisol, you can either start here to instead of using this route, you can use the other route here, where you can first carry out the dehydrogenation at position number 3 by the 3 beta hydroxysteroid dehydrogenase to form your progesterone. Then you carry out hydroxylation of position number 17 of the progesterone by the 17 alpha hydroxylase to form 17 alpha hydroxy progesterone. Then once you form your 17 alpha hydroxy progesterone, you hydroxylate again at position number 21 by the 21 hydroxylase. Okay, as shown here. Here. Then once you hydroxylate at position number 21, it will form your 11 deoxycortisol. Then you hydroxylate again at position number 11 for, here by the 11 beta hydroxylase to form now your cortisol. Remember, 11 beta hydroxylase is a mitochondrial enzyme. Okay, so this is your cortisol. And please note that glucocorticoids and mineralocorticoids have 21 carbons. Okay, have 21 carbons. Please note that. So I hope you have understood this, how you synthesize them. Okay, and here in yellow are your progestagens. I hope you can see this, and they are composed of 21 carbons. Your progestagens. Okay, here they are in yellow. But today you must know how aldosterone is synthesized and glucocorticoids are synthesized. This will occur in your zona fasciculata. Okay, so the zona fasciculata will not have the aldosterone synthase. Now, let's look at some of the congenital adrenal hyperplasias. Here we start with the cholesterol. Then to form pregnenolone, I said you use desmorase or your cholesterol side chain cleavage enzyme. Okay, you can see it as a member of the CYP. But for us to form a progesterone from pregnenolone, remember you need your 3 beta hydroxysteroid dehydrogenase, and it is not a member of the cytochrome P450 monooxygenase. And its deficiency will there will be, because you cannot form a progesterone, there will be virtually no glucocorticoids, mineralocorticoids, or active androgens or estrogens. So because you have no mineralocorticoids, there will be salt excretion in urine. Okay, and because you have no androgens, the genitalia will be female-like. So the males will have ambiguous genitalia. Okay, now if you have 17 alpha hydroxylase deficiency, okay, 17 alpha hydroxylase will convert your progesterone to your 17 alpha hydroxy progesterone. So there'll be virtually no sex hormones or cortisol. So there'll be increased production of, because if you don't have this, all this progesterone will be shunted towards aldosterone synthesis. So there'll be increased production of aldosterone, which will cause sodium and fluid retention, and therefore hypertension. Because you have no androgens, there'll be female-like genitalia. So the male will have ambiguous genitalia. Then you have 21 alpha hydroxylase deficiency, which is the most common form of congenital adrenal hyperplasia, occurring more than 90%. Okay, so please understand that 21 alpha hydroxylase is the most common form. There'd be partially or virtually complete deficiency, partially and virtually complete deficiencies known. So you can either have partial deficiency or complete deficiency. And the mineralocorticoids and glucocorticoids are usually absent. Okay, so if absent, that is the salt wasting classic form, but if deficient, it's a non-classic form. So if you don't have the 21 alpha hydroxylase, the progesterone and the 17 alpha hydroxy progesterone will be shunted towards formation of your androgens. So there'll be overproduction of androgens leading to masculinization of external genitalia in females. So females will have ambiguous genitalia, and they'll be very early virilization in males. Okay. Then moving to the last one, you can have a deficiency in the 11 beta hydroxylase deficiency. Okay, the 11 beta hydroxylase will convert your deoxycorticosterone to your corticosterone, which will further be converted to aldosterone by the aldosterone synthase. And remember, this 11 beta hydroxylase was a mitochondrial enzyme, and also the same enzyme will convert deoxycortisol to cortisol. So if you have deficiency in that, there will be decreased production of cortisol, aldosterone, and corticosterone, but there will be increased. Remember, deoxycorticosterone has aldosterone activity. Okay, so increased production of deoxycorticosterone will lead to fluid retention because it has some aldosterone-like activity. So there will be sodium and water retention. Okay, and also the hormone usually suppresses the renin, angiotensin, and aldosterone system, and this will cause, because you have low renin production, there will be hypertension. Okay, so hypertension can be caused either by deficiency in 11 beta hydroxylase or 17 alpha hydroxylase. Okay, now overproduction of androgen will cause muscularization and virilization, same as in 21 alpha hydroxylase activity. So I hope you have understood this. By just knowing where you have a deficiency, you ask yourself, if you don't have the enzyme which are after that deficiency, what will happen? And what will happen to the intermediates? The intermediates will be shunted towards the formation of the other steroid hormones. Okay, so I think that is that, and thank you for attention, and please subscribe for more anatomy and biochemistry content. Thank you.